Hey guys, in this video we'll talk a little bit about some asymptotes and kind of discontinuities in terms of limits, and just to help out with a little bit of what you might see in your problems today. So first, just a quick review of how do we describe an asymptote in calculus, and we describe it using a limit. So we have horizontal asymptotes and vertical asymptotes, and those of you who did the delta math with limits, or if you have done that already, saw some problems about these to begin with. But basically, if we have a horizontal asymptote, I can describe it in calculus by saying that's a limit as x gets really, really, really big, positive infinity, or as x gets really, really small, negative infinity. So as x approaches positive infinity, the limit of this function is b, because it's approaching this horizontal asymptote of y equals b. In this case, it's the same for both positive infinity and negative infinity because it's the same horizontal asymptote. If on the left side, let's say it approached a different number, a, then you would have had limit as x approaches negative infinity of f of x equals a. For a vertical asymptote, this time where x is not approaching infinity or negative infinity, x, the value of x along the x-axis, is approaching the asymptote, which is a. So at x equals a, we have this vertical asymptote. So from the left side of a, that's a with the little negative symbol, this graph is approaching positive infinity, so the y values, so we would say the limit as x approaches a from the left of f of x is infinity. On the right side of a, that's numbers bigger than a, but getting really, really close to a for x, the y values go down to negative infinity. And so, that's what we get as our limit there. Then, when we start to talk about some of the stuff algebraically, we kind of get to a couple of vocab words, particularly a removable discontinuity, and then an infinite or asymptotic discontinuity, which we just saw one of those in that last problem. So I've got two limits here. Limit as x approaches 3 of x squared minus 9 over x minus 3. If you remember, the first thing we would do is direct substitution. We would try it out and we see what we get. And we'd say we have 3 squared minus 9 over 3 minus 3. And so this evaluates to 0 over 0. And that has a special name in calculus. We call that indeterminate. And when that happens, that's a really good sign that we've got a removable discontinuity. On the graph, we think of that often as a hole in the graph. So that's a good sign that you should be able to do something algebraically here to get something to cancel out. And in this case, we see that it's factoring. So we would have as our next step here, limit as x approaches 3 of x plus 3 times x minus 3, factor the top over x minus 3, and those cancel. So then we have limit as x approaches 3 of x plus 3. And now I can go back to direct substitution. 3 plus 3 equals 6. So that's how we can evaluate that limit. On the other side here, we have one where when I try direct substitution, I get negative 3 over 0. This is undefined, which is a good sign that we have a vertical asymptote. So in this case, you might remember back to your pre-calc or algebra 2 days of this being a asymptote that diverges because it's x minus 2 to the first power. So in that case, we would know right away the limit doesn't exist. But I want to go through how we kind of algebraically show that, or really more numerically, because there's no algebraic, when you get 3 over 0 or anything over 0, when it's undefined, there's not going to be an algebraic way to simplify it like there is when you get 0 over 0. So we plug in numbers close, and we have to split it up into two here. We have to look at the left-hand limit and the right-hand limit. So we would say left-hand limit would be the limit as x approaches 2 from the left of negative 3 over x minus 2, and we can approximate it by plugging in something close. Well, the top stays negative 3, and the bottom is going to be like 1.99 approximately. Something like that. Well, that becomes a negative number and it's small. So we have negative 3 over negative small. Well, if we have big divided by small, we know that that's big. So this is going to be, and we have negative over negative, which is positive infinity. So we have positive infinity there. Now what about on the right-hand limit? Well, we would go limit as x approaches 2 from the right. And this time we plug in something like 2.01. So we still have negative on the top, but now we have a positive small. And when we do a negative divided by a positive small, we're going to get, and that should still be approximately equal to negative infinity. Since the left-hand limit doesn't equal the right-hand limit, we would say that this limit does not exist. Limit as x approaches 2 of negative 3 over x minus 2 does not exist. So hopefully some of that will help you out with your problems today from the AP website, and thank you for watching.